Now let's explore the concept of isomers. Isomerism is a property in which two or more compounds have the same chemical formula but different arrangement of atoms. Specifically, structural isomers are going to be compounds that have the same chemical formula, but they have atoms which have different bonding patterns. To give you an example, I'm going to draw the two structural isomers. In other words, the two constitutional isomers, which is another word for structural, that can be found for the chemical formula C4H10. In the chemical formula C4H10, we can draw the molecule butane, which this is the skeletal formula. And we can also draw two methylpropane. I'm going to zoom in and I'm going to convert these skeletal molecules into condense so you're able to observe how this turns into C4H10. As we learned previously in a skeletal formula, each end and vertex actually illustrates a carbon atom. So there's a carbon right here, one right here, one right here, and one right here in the molecule of butane. To incorporate the hydrogens, all I have to ask myself is, in order for carbon to have four bonds, meaning that's how it's going to reach its octet, how many hydrogens does it need to reach that? Starting from the carbon in the left, since it has one bond, it needs three hydrogens in order to reach octet. That's why the first carbon is a CH3. Second carbon, it has two bonds. That means that to reach four bonds, it needs two hydrogens. That's why it's a CH2. Similarly, the third carbon also needs two hydrogens to reach four bonds to reach its octet. The last carbon looks just like the first one. Since it only has one line, it needs three hydrogens to get to four bonds to reach its octet. Let me redraw this. There's a carbon right here with three hydrogens. So we can observe that in this molecule, I have one carbon, two carbons, three carbons, four carbons. That's where the C4 comes from. And when I add 3 plus 2, that's 5, plus 2, that's 7, plus 3, that's 10, that's where the H10 comes from. Let's look at 2-methylpropane. In 2-methylpropane, we have a carbon right here, a carbon right here, a carbon right here, and a carbon right here. Then let me add the hydrogens, starting from the carbon in the left. This carbon needs three hydrogens in order to complete its octet. The next carbon only needs one since it already has three bonds. The one that is pointing up needs three hydrogens. And then the one all the way to the right also needs three hydrogens. So when I count, this is one carbon, two carbons, three carbons, four carbons. That's where the C4 comes from. 3 plus 3 plus 3, that's 9, plus 1, that's the H10 in the chemical formula. Let me write the names of these compounds. This is butane. This is 2-methylpropane. And even though the atoms are added differently, these molecules are known as structural, or in other words, constitutional isomers of each other because they share the same chemical formula. One of the things about these structural isomers is that we don't have an equation that will tell us how many we can have. You can observe that, for example, for chemical formula C5H12, we only have three possible structural isomers. In C6H14, we have five structural isomers. But the minute that we get into larger numbers, like for example, C10H12, oh, sorry, C10H22, then we can have 75 structural isomers that can be developed. So the possible number of structural isomers just increases dynamically when we have more carbons in a chemical formula. That's why in organic chemistry, it is so important to draw structures rather than writing chemical formula because you can observe that multiple molecules can have the same chemical formula, but not the same structural attachment of the atoms. Additionally, we can observe that when it comes to these atoms, you can see here another illustration of the two structural isomers that I showed you before. Understand that isobutane is just another way that we write 2-methylpropane. So please do not confuse it. The 2-methylpropane is the IUPAC naming for it. This is just illustrating how you can technically start developing if you have the chemical formula for a particular group that you know that are isomers, how you can draw all of the isomers. Typically, whenever we're doing this, we always start with a straight chain alkane, as you saw me do in the example by drawing butane, and then we do the branch alkanes. I will encourage you that in order to practice, you are actually try to do the different isomers, for example, for C5H12, which only has three of them. Next, understand that one of the important things about isomers that even though molecules have the same chemical formula, their physical properties are going to be different. So let's see, for example, ethyl alcohol and dimethyl ether. Both of these molecules share the chemical formula C2, because we have two carbons, H6, because we have 1, 2, 3, 4, 5, 6 hydrogens, O, because we have one oxygen. And you can actually go through the same process and see that dimethyl ether is also a molecule that has the chemical formula C2H6O. Even though these two molecules have the same chemical formula, since the attachment of atoms is different, and particularly we can see here that these two are even different functional groups. The properties of these molecules are going to be different. While ethyl alcohol has a boiling point of 78 degrees Celsius and a melting point of negative 114 Celsius, dimethyl ether has a boiling point at negative 24 Celsius and a melting point of negative 141 degrees Celsius. So when it comes to it, understand that that's why it's so critical in organic chemistry that we do not write chemical formulas. We actually express our organic compounds as structures. Now we're going to look at cycloalkanes. Cycloalkanes or cyclic alkanes are going to be alkane chains that form a ring. The general chemical formula of cycloalkanes is CnH2n. We compare this to just straight chain alkanes, which their general chemical formula is CnH2n plus 2. And what this let us know is that what happens is that when it comes to cyclic alkanes, they have one less hydrogen on each terminal carbon compared to a straight chain alkane. In other words, every cyclic alkane has two less hydrogens compared to a straight chain alkane. There's many biomolecules that have cyclic alkanes in their structure. You can see that in figure 8.20, we have the structure of cholesterol. Cholesterol is an important biomolecule that is part of the cellular structure of the cells that we have in our body. And we're going to study this in detail, specifically in biochemistry chapters that have to do with fats. So later in the semester, we're going to revisit this structure. When it comes to cyclic alkanes, understand that their name is going to incorporate the word cyclo to represent their cyclic nature. When it comes to how do we represent in a condensed structural formula or skeletal representation for these molecules, we can see them specifically here in table 8.7. The smallest cyclic alkane that exists is going to be cyclopropane. Prop, which is a prefix that we learned before that represents 3 carbons, let us know that this cyclic alkane has 3 carbons. 1, 2, 3. We can have cyclic structures that have 4 carbons. The name of it will be cyclobutane. 5 carbons, cyclopentane. 6 carbons, cyclohexane. And additionally, we can have cycloheptane, cyclooctane, cyclononane, cyclodecane. It all depends how many carbons you have in the molecule. Notice that when the condensed structure is written for a cyclic alkane, it does not disrupt the cyclic nature of the molecule. So when we look more closely here, we see the interconnection of all the carbons in the cyclic molecule. Make sure that you review and you know how to draw both condensed and skeletal representations of cyclic alkanes. When it comes to naming, understand that specifically, if we have a cyclic alkane and there's only one substituent in it, the way that we write that name is that we write the name of the substituent followed by the name of the cyclic alkane. So in the following example, we can observe that we have a cyclic alkane of 5 carbons. There's 1, 2, 3, 4, 5. Since there's 5 carbons in the system, this represents a cyclopentane. And even in the structure, we can already see that it looks like a pentagon. Then we have a bromine as the substituent. Bromine as a substituent is a bromo group. So this is bromocyclopentane. Now we are going to proceed to learn about unsaturated hydrocarbons, starting with alkenes. We learned when we were first introduced to functional groups that alkenes are going to be the functional group that contain one or more carbon-carbon double bonds. Since carbons are going to be double bonded to each other, this results in alkenes having two hydrogens less than straight chain alkanes. So when we look at their general chemical formula, they're going to have the general chemical formula of CnH2n. That chemical formula we just observed that is found in cycloalkanes. But this just means that if you have a cyclic alkane and an alkene with the same chemical formula, then they're going to be constitutional isomers of each other. Alkenes are naturally occurring molecules. To give you an example, in figure 8.24, we have the example of ethene, which is a plant hormone that controls growth and fruit development and is at times utilized to artificially ripen fruits. Now we're going to proceed to learn how to name alkenes, but understand that some of the rules that we practice and learn when naming alkanes can also be used in naming alkenes. When naming alkenes, let's understand that specifically you're going to find the longest carbon chain that contains the carbon-carbon double bond. When we number the chain, we have to number it so we start at the end that is closest to the carbon-carbon double bond. When we write the parent chain, we are going to take out the ending "ane," and when we have alkenes, the ending is going to be "ene." We have to locate the first carbon in the carbon-carbon double bond, and we are going to write that number preceding the root and the ending. If there are substituents in the molecule, they're going to be written as a prefix, like we learned before, giving their location and additionally given their name. Let's look at the two examples that we have in the bottom of the slide. When we look at this alkene, we can observe that there are at least two parent chains that we can find. We can have this one, or we can have this one. Regardless of which one you select, you will obtain the same name. If I take this as the parent chain, I have to number it starting from the right side. This is carbon 1. Let me change the color of this. This is 1, 2, 3, 4. Since there are 4 carbon atoms, that means that the root is bute. Since this is an alkene, the ending is "ene." The first carbon in my double bond is at position 1, and I have one substituent. So the substituent is going to be at position 3. I have a methyl group. And that is placed before the location of the first carbon in the double bond, the root, and the ending. So this molecule, the name is 3-methyl-1-butene. Let me just highlight the different features so you see where they came from. The CH3 is the methyl group. Its location is here. This location is where we have the first carbon in the double bond. Since we have 4 carbons, that's where the bute comes from. And since it's an alkene, that's why it ends in -ene. Let's look at the next example. In the next example, we are going to first find the longest continuous chain. Remember that we're going to number it starting from the end that is closest to the double bond. So when it comes to this, if we number this from left to right, we find that that double bond is at position 1, 2, 3, 4, 5, and 6. Let me move the 4 down. But if we number this, oh, let me just move this one also. But if we number this from right to left, we notice 1, 2, 3, 4, 5, 6. So regardless which way we number it, left to right or right to left, this is going to be a 3-hexene. But when we have a alkene that is equal distance, meaning if I number it in both directions, the alkene has the same numbering, only then I'm going to choose the numbering that gives the substituents the lowest number. Only in that case. So when that happens, I need to specifically start numbering from the left to the right to give the substituents the lowest number. You can notice that if I number them from right to left, the methyl is going to go to 2, but then the fluorine is going to get a 6, which in the direction left to right, I will be giving the fluorine a position of 1 and the methyl a position of 5, which that is lower number. So let me erase this numbering. And then I have to put them, since they're different substituents, in alphabetical order. Let me highlight the parent. So this is my parent chain. So the complete name for this molecule is going to be 1-fluoro, because F comes before M, 5-methyl, 3-hexene. One of the interesting thing about alkenes is that these molecules can actually arrange in that double bond on the same side of the double bond or on different sides of the double bond. This is what I mean. Let's look at the example that we have specifically on the right side of the slide. We just learned how to draw alkenes, or how to name them, I should say. But drawing them, make sure that you practice it, is not that difficult. Let's say that we have 2-butene. Butene tells me that I have 4 carbons in a row. 1, 2, 3, 4. Next, since I have a 2 before the butene, that means that there's a double bond in between carbons 2 and 3. If I fill in the hydrogens in here, this is a CH3, this is a CH, this is a CH, and this is a CH3. Interestingly, it has been seen that the 2 CH3s that are connected to carbons that are double bonded can be facing the same side of the molecule, or they can be on opposite sides of the molecule. When that happens, let's understand that these are going to be specifically what we call in organic chemistry stereoisomers of each other. This is different from structural isomers. And what occurs is that thanks to this double bond that is unifying the two carbons in an alkene, all of a sudden having that trigonal planar geometry on those carbons gives us the ability to have different types of isomers that now they're going to be having different connectivity, but this different connectivity is in terms of space. Okay. Now, cis and trans isomers can only be found in double bonds, or meaning in alkenes for the context of our course, okay? The double bond that we find in the molecule is going to prevent rotation around that bond, so you cannot rotate from a cis alkene to a trans alkene. These are going to be two distinct molecules, okay? Now, let's see how we apply this concept of cis and trans to naming specifically alkenes. I'm going to first go back to the examples that we just did for naming alkenes to represent that not every alkene has cis and trans isomers. So let's go back to the two examples that we have here. I'm going to redraw the skeletal formula for 3-methyl-1-butene to actually look at it more closely. So I'm going to do it right here in the corner. If I draw the skeletal formula for 3-methyl-1-butene, what I see is that 3-methyl-1-butene says that I have 4 carbons in a row. 1, 2, 3, 4. Between carbons 1 and 2, I have a double bond. And because at position 3, my vertex is pointing up, the methyl will also point up. So this is where I write my methyl group, okay? Essentially, when we're trying to determine cis and trans stereoisomers in alkenes, what we have to do is look at the carbons that are connected in the double bond. So here we have a carbon, here we have a carbon. Then we look at what are the atoms connected to each of them. So the carbon on the left is connected to a carbon atom that has a hydrogen, and this is a CH3, and this is a CH3. This carbon atom is also connected to a hydrogen. Let me write it in. The carbon in the double bond that is all the way at the end, which is carbon number 1, is directly connected to hydrogen and hydrogen. Okay? To determine cis and trans, the steps are the following. You're going to take your alkene and you're going to create a division line between the carbons in the double bond. Then you're going to compare what are the atoms that are directly attached to each of the carbons in the double bond. We're first going to do the left side of the molecule. This carbon atom is connected to a carbon versus a hydrogen. Okay? Next, I have to ask myself, which one of those atoms, either the carbon or the hydrogen, has the highest atomic number? Looking at the periodic table, carbon has the highest atomic number when compared to hydrogen. So I'm going to label specifically the carbon, that area of the molecule, meaning this whole thing that is pointing in this direction, as high because the carbon has a high atomic number compared to hydrogen, and hydrogen is going to be labeled low because it has a lower atomic number compared to carbon. I'm going to do the same process on the right side of the molecule. On the right side of the molecule, I'm comparing hydrogen and hydrogen. So, since I have the same atom on the right side of the molecule, I cannot do the high atomic number versus low atomic number symbolism. So that means that 3-methyl-1-butene does not have cis versus trans isomerism. Let's look at the other example that we were looking at to see if indeed we can define if it's cis versus trans. If we look at the following molecule, we can observe that carbons 3 and 4 are the ones that are holding, that are unified by a double bond. So here there's a carbon, here there's a carbon. My hydrogen on carbon 4 is pointing up, while on carbon 3 is pointing down. Remember that when you have a double bond, those atoms are locked into those positions. So if I could do the same exercise and I take my molecule, I divide my alkene, and I look at what are the atoms connected specifically to the left of the double bond, to the right of the double bond, I can observe that to the left of the double bond, I have a carbon connected to two hydrogens. So when I'm comparing what is connected to carbon 3, I'm going to say, well, I have connected a carbon versus a hydrogen. And since those atoms are different, then I can ask which one has the high atomic number. And in this case, it's going to be carbon. So I'm going to label that position as high versus the one pointing down, that is low. Next, I'm going to move towards the right of my double bond. In this case, I'm looking at a hydrogen in this direction versus a carbon with a hydrogen in this direction. So if I'm standing on this carbon, I see that it is connected directly to a carbon, while in the other direction it's connected to a hydrogen. Carbon has a higher atomic number compared to hydrogen. So that means that when it comes to doing the high and low, this area of the molecule will be labeled high versus this area of the molecule will be labeled low. Taking that into consideration, if I tilt my head a little bit to the left, I can see that the words high and low are not pointing both up or both down. The high is pointing across and the low are pointing across. That means that this alkene is a trans stereoisomer. Another symbol that can be used for trans is just the capital letter E. Let's do one more example to solidify this concept. Let's name the following alkenes. If we look at the first alkene, my longest continuous chain of carbon atoms is this one, where we have 1, 2, 3, 4, 5 carbon atoms. So this is 2-pentene. And at position 2, I have a fluoro group. Next, I'm going to see what are the atoms that are connected to the carbons that are double bonded. I have a carbon right here, and I have a carbon right here. Let me divide my alkene in half. Towards the left of the molecule, this carbon is connected to fluorine versus this carbon is connected to carbon. So when I compare fluorine and carbon, fluorine has a higher atomic number. So I label it high. Carbon has a lower atomic number, so I label it low. Let me look at the right side of the molecule. In the right side of the molecule, I have at carbon 3 a hydrogen pointing down. At carbon number 4, I have a CH2. So when I look at what is attached to carbon number 3, I'm going to say a carbon versus a hydrogen. So because carbon has a high atomic number compared to hydrogen, then it's going to get the high label versus hydrogen, which is going to get the low label. So if now, because my double bond is more towards the right, if I tilt my head to the right, I can see that now the highs are on the same side and the lows are on the same side. So that means that this 2-fluoro-2-pentene is the cis stereoisomer. Let me just change the color of this. And the one letter designation for cis is actually the letter Z. So this molecule specifically is cis 2-fluoro-2-pentene. Let's do one last example for this concept. Let's look at this one. First, we're going to take a moment and name the molecule, which to name this molecule, the parent chain is this. The number of carbons that we have here are 1, 2, 3, 4, 5, 6, 7, 8. So this means that the name of this molecule is going to be 4-isopropyl 4-octene. Let me write in the carbons and hydrogens. This is a CH connected to 2 CH3s. That's why this is an isopropyl group. It is out of position 4. Also on carbon 4 is where my double bond starts. So that's why I have this digit of 4. Oct for the 8 carbons, ene because this is an alkene. So if I look specifically at this alkene and I divide it in half, first I'm going to look at everything that is connected to the left of the carbon-carbon double bond. So if I look at this carbon, this is connected to a hydrogen, is connected to a CH2. So carbon number 5, I am comparing a hydrogen to a carbon. Remember that essentially, if you do the Lewis structure, you will see that the hydrogens are sticking out of carbon 6. So that's why I'm comparing carbon 6 to hydrogen. Carbon has a higher atomic number compared to hydrogen. So this area of the molecule is going to be labeled high, while the hydrogen pointing up is going to be labeled low. Let's now look at the area where carbon 4 is connected. I'm going to include the carbons and hydrogens. This is a CH2. This is a CH2. This is a CH3. Okay? So the atoms that are connected to carbon 4 are a carbon with 2 hydrogens and a carbon versus a carbon with 1 hydrogen and 2 more carbon atoms. So if I write them in a row, this area of my molecule is a carbon atom connected to 2 hydrogens and a carbon, while this area of my molecule is going to be a carbon with a hydrogen and a carbon. Let me highlight this again. So carbon, hydrogen, that's these two. And then this is connected to a carbon, that's that one. And this is connected to another carbon, that's that one. Okay? So when I'm trying to determine, okay, is the group pointing down or the group pointing up? Meaning this is the one that is pointing up. This is the one pointing out. Which one is preferred or gets the high label? The one that will get the high label is going to be this area. Because when we look at the arrangement of the atoms, we have to tell ourselves, well, carbon compared to carbon, same atomic number. Hydrogen to hydrogen, same atomic number. But when we compare carbon to a hydrogen, then we have to say, well, carbon has a high atomic number. So overall, a group like this is a higher atomic number. So here, the high label is in the bottom, low label is in the top. So again, if we tilt our head to the right because of the way that the double bond is written, notice low is on the topper part. Highs are in the lower part. Since they are on the same side, that means that this is the cis configuration for this alkene. Understand that the cis and trans isomers only exist in alkene molecules.